Hello, my name is Chris Harris and I'm from Allery Chemistry, and welcome to this video on an introduction to AS level organic chemistry. This is topic 13 for the CIE exam board, so it's the Cambridge Internationals. So this topic, obviously we're going to look through some organic compounds and the introduction of that, and look at isotopes and isomers and things like that, so various different organic substances. So if you are looking, if you're studying the CIE exam board, then this video is perfect for you, and obviously we'll go through topic 13. There are all of the topics for year 1 and year 2 A-level chemistry that are on the Allery Chemistry YouTube channel. Hit the subscribe button to show your support. That would be really good. Also, this video is made from PowerPoint slides which I've made, which you can purchase from my test store. If you click on the link in the description box below, you'll be able to get a hold of them there. They're great for revision and great to kind of supplement your notes and your books and everything else that you have with it. So go and have a look on there, and that would be brilliant. So let's make a start and let's see what this topic is all about. So obviously this is the kind of first part of the organic chemistry part of it, of year 1. So there's a series of organic chemistry videos for the rest of the topics up to topic 22, which includes the analysis bit as well. So this is kind of an introduction to that, but there is obviously quite a few videos that kind of fill in the blanks, I suppose. So what you need to be aware of with the introduction is basically the kind of what is organic chemistry, and look at the kind of basics of it and different isomers, and look at the formula and things like that. That's really what this is going to look at. So the first one is we need to know about different types of formula that exist, and the first one is a general formula. So a general formula is an algebraic formula that can be applied to chemicals in the family. So for example, alkanes, alkenes, alcohols, etc. So you can see this is obviously an algebraic formula. So alkanes would be CnH2n plus 2, etc., where n is a number, obviously. So this is what you call a general formula, and you'll see these terms kind of used throughout your exam paper and your notes, etc. Okay, so the next type is a molecular formula, and this is the actual number of atoms in a molecule or element. So obviously the actual number, as you can see, is, for example, this is for ethane, is C2H6. So obviously we've got 2 carbons and H, and obviously 6 hydrogens for ethane. So this is the actual chemical formula. Empirical formula is the simplest whole number ratio of atoms in a compound, and you might have seen this already in a previous topic. So example is ethane, which is C2H6, or the empirical formula for ethane would be CH3. So that's the simplest whole number ratio for ethane. Okay, so structural formula. So this is the arrangement of atoms in a molecule without actually showing all the bonds in it. So, for example, butan-1-ol is the structural formula for this would be CH3, CH2, 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 OH. So what we're showing here is the kind of chunks, the CH chunks in this molecule, but we're not actually showing the bonds in between. So this is an example of a structural formula. Okay, so a skeletal formula basically shows the bonds of a carbon skeleton only. So hydrogen and carbon atoms are not actually drawn in, but functional groups are. Now, the purpose of this type of formula is it's just much quicker to draw. So when you have a really long hydrocarbon chain with loads of carbons and hydrogens in, it can take ages. And as I've mentioned before, chemistry is about trying to cut down on the amount that you have to write, and there's a lot of acronyms, there's a lot of shortening of things, the formulas are no different. So this is ideal for things like organic chemistry because you draw a lot of molecules with loads of carbons in. So example, each point on a line represents a CH group. So for example, this would be CH3, that would be CH2, that's CH2, that's CH2, and then OH. So basically this is showing you 1, 2, 3, 4 carbons, and at the end you've got OH at the end. So this is butanol. So this is the same compound or the same substance that we'd seen just before. So these, you'll see these quite a lot actually, which is skeletal formula. Okay, displayed formula. So these show the arrangement of atoms, showing all the bonds and atoms in the molecule. So for example, this is 2-chloropropane. So you can see you've got all the bonds obviously shown here. So basically these are covalent bonds being shown. Obviously you've got chlorine there. So anything to do with displayed formula is basically what you would show all the bonds are displayed there. So it's really important you need to know these different types of formula, because they can ask you to give your answer in one of these types of formula. So you've got to be prepared to write it down correctly and make sure it's accurate. Okay, so they're all the formulas that you see there. Now what we're going to look at is something called a homologous series. So this is kind of like the family of different compounds. So homologous series is a group of compounds that have the same functional group and they have the same general formula. Okay, so let's have a look. You've got a general formula. We can use the general formula to work out molecular formula of a compound. So, for example, alkenes have the general formula CnH2n, where N is obviously the number of carbon atoms, as we've seen before. And the molecular formula of an alkene with 23 carbons would be C23H, which is 2 lots of 23, so that would be C23H46. Okay, so that would be effectively the general formula for that alkene. So successive members of the same homologous series increases by CH2. So for example, the general formula of alcohols is CnH2n plus 1 OH. So your homologous series would be obviously methanol. See, ethanol, you've added an extra CH2. Propanol, added an extra CH2, butanol, added an extra CH2. So basically, as you go across, you can see these are all part of the same family, so the homologous series, they're all alcohols, but you've got different types of alcohols. You've got methanol, ethanol, propanol, butanol, and the only difference is we're adding an extra CH onto that. So that's what we mean when we say homologous series, so it means the same. Okay, so homologous. So we're looking at similarities here. Okay, really important for organic chemistry is nomenclature. Okay, now this is where it can get a little bit tricky, and this takes practice. And really with these type of things, it's about writing down. You'll probably pick this up just through writing that many names of organic compounds, rather than specifically trying to remember how to actually name these. You'll kind of pick it up through habit because you'll do it a lot. So, molecules are named by a set of rules, and this is set down by IUPAC, which is basically the body that decides how chemicals should be named. And the reason why it exists is it just ensures that the naming of chemicals is universal, so that if you're in America, you know what one substance means, and you would understand what it means if you're in Britain, or if you're in Germany, or if you're in Japan or France or anywhere like that. The standard way of naming compounds, or the way of naming chemicals, is standardized, and that's why they call it IUPAC. So the first thing when we're looking at naming chemicals, there's a series of rules here, so we're going to go through some here. So we're going to find the length of the stem by counting the longest continuous chain of carbons. So here we've got the first 10 here, just to kind of give you a start. So number of carbons for 1 would be meth, and then 2 is eth or eth, 3 is prop, 4 is bute, 5 is pent, 6 is hex, 7 is hept, 8 is oct, 9 is non, and 10 is dec. So you've got these are the kind of stem names right at the start. Okay, and we are going to actually name this compound eventually using these rules, but we'll kind of start off with this. Okay, so in the middle, this compound here, how many carbons does this have? The longest continuous chain is 4 carbons. That's the longest. Okay, so this being the stem is bute for this one. So it's got 4 continuous. You could do it this way if you wanted as well. It doesn't really matter. No, it does actually. You'll see it in a minute. But this is the longest carbon chain anyway. So you ignoring this bit. Okay, so the functional group on the molecule normally tells you the ending of the name. So this is the suffix. So it also has an OH group, as you can see on here. There's your OH group. So this means it will end in ol, because this is an alcohol. Okay, so we know it'll end in ol. So number the carbon chains. The third thing we need to do is number the carbon chains so that the functional group sits on the lowest possible number carbon. Okay, so we can either number it as 1, 2, 3, 4 like this, or if we do it the other way, you can do 1, 2, 3, 4. But obviously the lowest number, the functional group here, sits on the lowest number, so that's got to be 1. So this becomes carbon 1 because that's obviously smaller than 4 if we numbered it the other way around. So then what we're going to do is make a note of the carbon the OH is attached to, which is 1, and we place this number before the suffix. Okay, and so this is a type of butan 1-ol. So the suffix is ol, because that suffix is obviously the end bit of the molecule, and it is sitting on carbon 1. So we're going to put butan 1-ol, which we can see on there. So that's what this is so far. Okay, and then the 5th step is if we've got any side chains and less important functional groups, these are written as prefixes in alphabetical order. Okay, so here you can see that obviously we do have a methyl group that's sat here on the 3rd carbon. So you can see if there's more than one identical functional group or side chain, we put di, tri, or tetra in front of it. So in this case, this is 3-methyl, because we've got a methyl group there. That's your CH3 on the 3rd carbon. Butan, because you've got 4. And it's 1,1-diol, because we've got 2 alcohol groups there. Okay, so because we've got 2 of them, we put di, which is on there. So that's 2, and it's ol. And we basically number as 1 and 1. That basically tells us that the 2 alcohols are on carbon 1 and 1. So they're basically bonded to the same carbon, as you can see there. But we always do it in alphabetical order. Okay, so, and then we have this methyl group hanging off the 3rd carbon. That's why it's 3-methyl butan 1,1-diol. Okay, so this, obviously I've given you this example here just to show you various different groups that are in this molecule. You will see, and obviously you'll see me kind of go through these videos and the future videos to do with organic chemistry, naming these compounds. The key thing with this is just to make sure you've got this to hand, especially when you're writing these out for the first time. Make sure you've got these rules to one side, and whenever you're going to write a molecule, try and follow these rules, and then, you know, hopefully through habit of writing these out that many times that it'll become kind of second nature, hopefully. Okay, so let's look at some functional groups. Obviously, we've seen one of them there at least, which is an alcohol, but there are loads of other functional groups in chemistry. So you need to know quite a few functional groups actually, but we're going to split it down so that you know the ones for AS level first, and there'll be some additional ones that you need to know for A level as well, but that will be later on in a further topic. So functional groups, these are kind of groups of chemicals which have a unique kind of reactivity features, so they're called functions. Okay, so these are really important in chemistry because obviously your functional groups, different functional groups will react differently and they will interact differently, so you get multiple different reactions depending on the functional group that you have. So let's have a look and see what some of these are first. So we'll start with the simplest one first, which is an alkane. So obviously the prefix of the suffix is ane, for example propane, and that's the general formula. Alkenes have the double bond in between it, so it's C double bond C. They end in ene, so it might be methane. It might be ethene, propane, or propene, butene, for example. And propene is obviously an example there. Alcohols and diols, as we've just seen just there before. So alcohols have an OH on the end. So they end in ol. sometimes they can be hydroxy as well. So it just depends on how it's written. So sometimes instead of putting all at the end, it can be hydroxy instead. So for example, it might be methanol as an example. Okay, so haloalkanes, you've seen some of them already probably. So haloalkanes basically just have a halogen attached to it, and the prefix or suffix would be fluoro, chloro, bromo, iodo. So they come at the start in this case, because so it's a prefix, sorry, so they come at the start. So for example, bromopropane. So if there's a bromine on there, then it'll be the halogen and then the alkane that's attached to it. Ethers. So these have, there's a bit of a funny one. They basically have a oxygen in the middle. So you might have two alkane groups with an oxygen in the middle, and these are called alkoxy. So you might not have that many of these, to be honest, but an example would be methoxymethane. So for example, that's obviously a methyl group and a methyl group there, and there's an oxygen in between. So it's methoxymethane. Primary amines, diamines. So you might see some of these as well. So they have a obviously they've got an NH2 at the end of them. For example, you probably call them amino or amine at the end. So for example, aminopropane, or you might say diaminopropane, or you might even see it as methylamine, for example. You might see amine at the end. So basically these have an NH2 group at the end of a molecule. Okay, aldehydes. So aldehydes have this double bond carbon, so the C double bond O with an H, and they end in al, so it might be methanal, butanal, propanal, for example, or ethanal is an example there. Carboxylic acids and dicarboxylic acids. So these have very similar to an aldehyde, except instead of an H, they have an OH at the bottom here. So these normally end in oic acid. So it might be methanoic acid, ethanoic acid, for example. Sometimes they're known as carboxy. You can use it as a prefix as well, but the vast majority of the time you're going to see it as oic acid at the end. Okay, esters. So these are, again, very similar to a carboxylic acid. They have this double bond O with an R group there. So they end in O8, for example, methyl ethanoate. That's an example of an ester. Ketones. So ketones have this C double bond O group, as you can see on there. So they normally end in -one. So for example, propanone, butanone, etc., etc. So that's a ketone, similar to an aldehyde. Nitriles basically end in CN, so it's either cyano or nitrile, as you might see it as. So an example would be ethane nitrile, so that would be a CN compound there. Okay, so there's a lot of different substances there. The best thing to do really is you'll see a lot of these kind of come back into throughout the topics in future. It's really just to kind of introduce them to you really at this stage and just show you what's there. Okay, so let's have a look at bond fission. Okay, so bond fission is, fission means to break something. Okay, so when you're looking at organic chemistry, you're going to be breaking bonds all the time for chemical reactions. And there's two types of fission that you need to know. You've got homolytic fission and heterolytic fission, and one is probably more common than the other. But bond fission, like I said, is the breaking of a covalent bond, and the electron pair in that bond can be distributed in a couple of ways. So let's look at heterolytic fission first. So heterolytic basically means different. Okay, so we're breaking the bond, but the electrons in that bond are distributed unequally, okay, to form two different ions. So we get a cation and an anion. So a heterolytic meaning difference. So we've got a difference in where the electrons are. So in this case, we use a double-headed arrow, and again, you'll see this throughout organic chemistry quite a lot. We get double-headed arrow, and basically this shows the movement of a pair of electrons from the bond going to one molecule or the other, and the result is, as you can see here, you've got Y, which has got Y minus, and X, which has got your X plus, which is there. Homolytic fission is basically where the bond, the electrons in the bond are distributed equally. So the bond breaks with a pair of electrons being shared equally, and actually we form radicals instead. So we've got a little dot on the top there. So that means we've got an unpaired electron, and obviously homolytic meaning it's been split the same. Okay, so it's the same. It's an equal split of them electrons. Okay, so let's have a look at one of them types. And one of them we said was homolytic fission. And a classic example is a free radical reaction that is actually an example of a homolytic fission. Now, free radical reactions are, it sounds quite extreme, doesn't it? A free radical. So free radical reactions are actually involved in three broad stages that you need to be aware of. So one of them is what you call an initiation stage of a reaction. You've got the propagation stage, and you've got a termination stage. So you've got three different stages to these reactions. Now, initiation, as it suggests, is how you actually kickstart a reaction. So radicals or homolytic fission is generally started by using UV light. And effectively, this is what you call a photochemical reaction. So UV light helps to split the bonds. The electrons move to form a radical, or form two radicals, just as we've seen before. So this is an example of homolytic fission. Propagation is basically when a radical reacts with a non-radical molecule. So in other words, a non-radical. New radicals are created, which then go on to react with other non-radicals, and this is why we call it a chain reaction. So it basically keeps reacting and reacting. As long as you've got a radical and non-radical, you'll always produce another radical. And we'll go through an example just to show you this as well. And obviously termination means to stop. This basically means the chain reaction stops. And the only way you can terminate a reaction is by having two radicals reacting together, and they form a non-radical, which is then ends that reaction, so ends that chain. And this is why it's obviously called termination, so it ends. So let's have a look at an example, and we're going to look at an example here. I'm going to introduce you to one of the first functional groups. This is a halogenoalkane, also known as a haloalkane, and this is going to use that free radical process that we mentioned there before. So chloromethane is a chemical that can be used using UV, and it's an example of homolytic fission. So CH4, which is methane, reacting with chlorine to form CH3Cl, that's your haloalkane, so chloromethane in this case, that's chloro and then methane, and that will form hydrogen chloride, so HCl. So initiation, so the first step is we need sunlight, or UV basically, to break the bond, and we're going to break it equally, producing two highly reactive radicals. Okay, so we're going to break this Cl bond here, the Cl-Cl bond. So the UV is going to come in and break that. So there it is. So break that bond and we form two radicals. Okay, so that's your initiation done. Nice and straightforward. The next step is the propagation stage. So this is where you've then got the radical is incredibly reactive. Okay, really reactive. It will literally react with anything. And the Cl radical reacts with methane that's knocking around here. There it is. And this will make a methyl radical, which is CH3 dot. So the hydrogen kind of gets pulled off and you're left with the radical. And the methyl radical then reacts with the Cl2, because you'll still have some Cl2 floating around in there. That reacts with the Cl2 molecule, forming chloromethane and a Cl dot radical. And then this Cl radical can then react with more methane. And you can see kind of it just keeps on going and going and going. So let's split this up and have a look and see what it looks like. So you can see there's your Cl dot, there's your radical that was formed in the initiation stage. It reacts with the methane molecule that's just kind of floating around here. And then effectively the chlorine radical nicks the hydrogen, or takes the hydrogen I suppose, to form HCl. But then you've got another radical here, which is CH3 dot. Here's another one. That CH3 dot will then react with Cl2, which you'll still have some of this around. That will form CH3Cl. There's your haloalkane. and then you form your Cl dot radical, and you can see that can then go back and start the process again, and this will carry on and on and on and on until you get to a termination stage, and this is where two radicals, any radical here, will collide to make a non-radical molecule which is stable. Okay, so for example, you could form chloromethane here. So there we are. So you've got a CH3 dot and a Cl dot. If these two combine together, they form this, which is your chloromethane molecule. So again, you formed it here. That's not a radical, and that stops the chain. Okay, so this is an example of homolytic fission because the electrons have been moved equally from one side to the other. So products, so obviously producing just chloromethane is actually quite difficult because, as you've probably seen for some of these reactions, you get further reactions that occur and you actually produce a mixture of different products. So there's loads of chlorine in the reaction mixture. If there's loads of it anyway, then we'll get di, tri and tetrahaloalkanes, so we'll get multiple substitution. So if we look at this example here, you've got Cl dot reacting with chloromethane that we've just made. It creates a radical, so remember it takes the hydrogen from there, so you've got CH2Cl dot plus HCl. That radical will then react with more chlorine to form CH2Cl2 and Cl dot. So you form dichloromethane here is formed, so you've got two chlorines on there. And then guess what? It can go further, and that CH2Cl2 that you formed here can then react with more chlorine radical to form CHCl3, so you form trichloromethane. And then trichloromethane can obviously react further to make tetrachloromethane. So you can see how this just keeps going. It's almost uncontrollable. And obviously, with free radical substitution, you're making chloromethane, dichloromethane, trichloromethane, and tetrachloromethane, which all of these have to be separated if you want to just have one product. So this is a pretty efficient reaction, but it's haphazard. It just produces so many different products because it just keeps on reacting. That's why, because your radicals are really, really reactive. So adding excess methane, okay, when we add to this reaction here, if we add excess methane, this will reduce the amount of multiple substitutions because you've got a greater chance of chlorine reacting with the methane, and that's the only way in which we can try and control this or try and reduce the likelihood of multiple ones. So in addition, obviously, to these multiple substitutions, we can also get isomers formed, and we'll look at isomers a little bit later on. And this is because free radical substitution can occur anywhere on a hydrocarbon chain. So, for example, if you had a longer molecule, such as butane, butane's got 4 carbons, you can have a chlorine at the end, you can have a chlorine in the middle, you can have 2 chlorines in the middle, 1 at the end, 1 in the middle, 2 in the end. You have loads of different isomers that are formed, but we will look at isomers later on because that's obviously going to be quite important. So it's just understanding what these free radical reactions are that's going to be quite important. Okay, so let's have a look at some other reaction types. So obviously that's an example of homolytic fission. So the reactions actually, so different chemical reactions can be split into 7 broad groups. And again, this is just an introduction. You will go into these reactions into a lot more detail, obviously later on when you go into specific examples. But just to introduce them, you've got addition reactions, and this is a double bond is broken and 2 molecules join to form a single product. And the functional groups involved are alkenes, for example. You've got aldehyde groups here, or could be ketones, for example, or that's your aldehyde, sorry, and ketones or alkenes. So you've got all these different functional groups. These can get involved with addition reactions, so you can add things onto these. These double bonds can open up, basically. Substitution reactions, so this is where a functional group is exchanged for another one, so hence substitution. And so these could be, for example, halogens, and you could substitute a hydrogen in a benzene ring. You won't see this until year 2, so don't worry about it if you just do an AS. Or alcohol groups, you have OH groups, so these can be substituted for something else. Elimination or dehydration reactions. So this is normally where you have a double bond is normally formed. So you've literally removed an element of a molecule and you have to form a double bond to kind of keep the integrity of the octet rule going. So normally a double bond is formed when a functional group is removed or released as part of a smaller molecule. And generally the type of substances which are removed are halogens. For example, X or HX can be eliminated, or water can be eliminated from a molecule. So that's why they're sometimes known as dehydration. Okay, so let's look at some more reaction types. So condensation reactions. Now, obviously, condensation reactions kind of make sense. This is when two molecules join and a small molecule is eliminated. Generally, this is water because it's condensation, but it could be HCl, for example. Yeah, it can be HCl, so even though it's condensation reactions. So the functional groups involved generally here are, this is called acid chlorides. Again, you won't see these until year 2. Carboxylic acids, amides, you won't see these until year 2, or alcohols. Okay, so you've got various different types of condensation reactions. Hydrolysis, now hydrolysis, hydro means water, lysis means to break. So these are just reactions where you're splitting molecules up using water, hence the word hydrolysis. So two smaller molecules are formed by splitting a larger one with water, such as breaking polyamides or polyesters. So these are your polymers, which you'll see later on in year 1. And the functional groups involved are generally things such as esters, for example. So these could be a classic example of just polymer chains. Okay, and the final one is, the penultimate one, is oxidation. So we've seen oxidation before, you've seen it in one of the previous topics, but normally this means gaining of oxygen or the loss of hydrogen in reactions. However, theoretically, it's obviously the loss of electrons, so you'll remember that. So OILRIG, that's the acronym I think we used. So oxidation is the loss of electrons, reduction is the gain. So the functional groups normally involved in oxidation are things such as alcohols, aldehydes, carboxylic acids, and alcohols forming ketones, for example. So you'll see these later on in like I say, in year 1 chemistry. And your final one is then reduction. So it's obviously just the opposite of oxidation. So this normally means the loss of oxygen or the gain of hydrogen in reactions. Obviously, in reality, this is the gain of electrons. So reduction is the gain of electrons. So the functional groups normally involved is just backwards. Is the other way of what we see with oxidation. So carboxylic acids going to aldehydes, going to alcohols, or ketones going to secondary alcohols. But you'll see a lot of these, again, don't worry too much about these. You think, what on earth is he talking about? You will see a lot of these reactions in future topics. It's just to introduce them to you. Okay, so let's have a look at some attacking agents. So this sounds quite violent, doesn't it? There's attacking agents and free radicals and things like this. So there's a lot of different kind of these are chemical reactions, so you're going to have like groups being attacked and things like this. So types of attacking agents. So you need to know the type of attacking agent that you're dealing with, and you'll see a lot of attacking agents throughout chemistry. So one type of attacking agent is called an electrophile. So electrophiles, these are electron-loving species. So they're generally positively charged ions, and they attack other molecules that have a negative charge, or they might have a delta negative. Now, you would have seen this before when we looked at polarities. So when we looked at polarities in molecules, so electronegativity and things like that. So you get delta negatives there. So examples include NO2+, CH3+, H+, like acids, CH3CO+, and sometimes you can get Cl+, Br+, I+ as well. So you can get these different types of substances here. Another type are nucleophiles. So these are nucleus-loving species, and so these must have, because remember nucleus is positive, so these have got to have a lone pair of electrons. Okay, some may have a negative charge, but nucleophiles must have a lone pair of electrons. So they attack other molecules that have a positive charge or delta positive. So examples of nucleophiles are OH minus, NH3 because they've got lone pair of electrons, water, cyanide molecules, so CN for example. They must have a lone pair of electrons though for them to be nucleophiles. And the last type are radicals. So as we've seen these before in the previous reactions, so these are atoms with an unpaired electron and they're incredibly reactive. As you can see, they produce loads of different types of products. They're initially formed via UV light, so that's how we normally make them. So examples are Cl dot, CH3 dot and Br dot. So they're different types of radicals. Okay, so just to kind of touch on this, because I know we've seen this before under the bonding topic, but this just really kind of brings it back in and just puts it into a little bit more context. So I'm not going to go into a lot of detail on this, and the best thing to do is to go back to the bonding topic, which I think is topic 3. So it's the bonding, structure and bonding topic. So this is really just to kind of bring this back in again. Just briefly, but when you have organic compounds, they do obviously have covalent bonds. Mostly are covalent bonds, and you do have what we call sigma and pi bonds, as you've already seen before in the previous topic. So just to kind of cover this, or just to kind of go through it again. So when you've got bonds, just briefly, so when you've got a bond, you have to have orbitals that overlap. And so remember, you have s orbitals and you have p orbitals. They're the kind of main orbitals. You do have d and f orbitals, but the main ones are s and p orbitals in relation to carbon-hydrogen bonding, which is effectively organic chemistry. So when they bond, these have got to overlap. Okay, so these bonds must overlap with each other. Now, quite often, what you get is you get bonds which kind of merge. The s orbitals and the p orbitals merge to form hybrids. Okay, so you form these different kind of hybridization. So with sigma bonds, so sigma bonds are actually formed. These are the single bonds that you see in organic compounds. These happen when you've got two orbitals that overlap. And in the CH bond, so in the CH bond seen in topic 3, that's the topic you must go back to if you really, because I'm not really going to go into a lot of detail on this in here. You should visit that topic there, that video, to see what I'm talking about here. But effectively, the CH4 has 4 sigma bonds, okay, with some S and some P characteristics. And we form this hybrid of an sp3. So just as a quick reminder, we have an s orbital with 3 p orbitals. And we form these new hybrid. These are hybrid orbital, okay? And the bond angles in something like CH4 is 109.5, okay? So that's the bond angle there. So another type of hybrid is where basically the s orbital in the carbon is hybridized with only 2 p orbitals instead of the 3 like we would see in alkanes. So, and these are normally found in alkenes and in benzene, but you'll see benzene in year 2. So what we can have is we can have 3 lots of what we call these new hybrid molecules, the sp2 orbitals, and we have a p orbital that kind of sits top and bottom, so it sits in the polar orbit there. So the sp2 orbitals sit at 120 degrees to each other, and they form this planar structure, with the remaining p orbital at 90 degrees, like I say on there. Okay, so this is if we have, say, an alkene. So with alkenes, remember these have got the double bond, okay? So you have a pair of the sp2 orbitals, so that might be in this molecule, that might be a carbon atom. Let's say, for example, these are the orbitals in it. So there might be another carbon atom here that will kind of interact and overlap its orbitals with that one there. And it's that forms the sigma bond. So when you've got the merging of this sp2 hybrid orbital here, that will merge with that forms the sigma bond, and that starts to pull the atoms closer together. And actually what you then have is these orbitals on the top here. So remember you had this orbital, kind of the p orbital that isn't hybridized on the top here. Now this can then overlap with the carbon atom next to it, and it can form this, and this is called a pi bond. So a pi bond is effectively, it's not the hybrid orbital, it's the p orbital that was left, behind that kind of merges with the neighbouring p orbital in the next carbon atom, and it forms this kind of looks like a hot dog bun shape orbital, and this is your pi bond, and the pi bond is effectively the double bond. So you have a sigma bond in between the two, and then you have this pi bond that's kind of over the top there. Okay, so remember these exist 90 degrees to the sp2 orbital, so they're kind of on the top and the bottom, like there. So your p orbitals are dumbbell shaped, and when they merge, they form two oblong shapes. So you can see them there. So that's them kind of buttoned together, and then these two orbitals that were 90 degrees to that then merge to form the pi bond, as you can see there. So this is an example of a double bond, an alkene. Obviously, an alkane will just have the sigma bond in between the two. Okay, so alkanes will bond via sp3 hybrids. So obviously you need 4 of them. Alkenes will bond via using sp2 hybrid orbitals. Like I say, I can't emphasize this enough. Go back to topic 3 if you're not sure what this is talking about. I'll go into a lot more detail and explain what they mean. It's probably a good idea to visit that first and then come back to this particular part of the video if you wish. Okay? It is tricky, by the way, so it isn't straightforward. Okay, so let's have a look at some isomers. I did say we're going to have a look at some isomers here, so we're going to look at some of them here. Now, there's a few of them, so we're going to start with one of them, which is called a chain isomerism or chain isomer. Now, these are called structural isomers. Now, you need to know what a structural isomer is. So, structural isomers have the same molecular formula, but they have a different structural formula. And there's 3 types of structural isomers. Okay, you've got chain, positional, and functional group. Okay, now the word chain, positional, and functional group tells you what's changing in that isomer, so what makes it different. So obviously chain isomerism is the chain is changing, so the actual molecular formula is the same. Okay, so there's no difference in there, but we're changing the position of some of the atoms on a longer chain. So let's have a look at a particular example. So your chain isomer, same molecular formula, but different arrangement on the carbon skeleton. So let's have a look at this one. This is pentane. Okay, fine, 5 carbon atoms in there. This one is 2-methyl butane. Now, this is exactly the same molecular formula. In other words, it's got the same number of carbons and hydrogens in here. But what we've done is we've just shuffled some of it around. We've changed the shape of the chain. Okay, so the chain has changed. So you can see here, this is obviously the longest carbon chain here is butane. So you've got 1, 2, 3, 4, as you can see there. And obviously the methyl group, this one here, is sitting on the second carbon, so 2-methyl butane. So that's a different molecule to pentane, but it's got the same number of carbons and hydrogens. So that's a chain isomer. Okay, let's look at the next type of isomer, which is positional. So a positional isomer. So positional isomers, as it suggests, is the same molecular formula, but there's a different position of the functional group. Okay, so the chain might be the same, but the position of the functional group will be different on the carbon skeleton. So let's have a look at this one here. This is pentan 1-ol. So you've got an alcohol group here, and that's on the first carbon there. Okay, so if we look at its isomer, this is pentan 2-ol. So all we've done is we've kept the same chain hasn't changed, but the alcohol group has moved from carbon 1 to carbon 2. Still the same functional group, it's just changed the position on the chain. So that's what we call that as a positional isomer. Okay, so let's look at the last type of structural isomer, which is a functional group isomer. So it's the same molecular formula, but it has a different functional group. So we're actually changing the functional group completely. So a classic example, pent-1-ene. So this is an alkene. Okay, so it's got that C double bond as an alkene. And that can form cyclopentane. Now, you can see here, if you count the number of carbons and hydrogens, it's exactly the same as pent-1-ene. But it's no longer an alkene anymore. It's a cycloalkane. So it's basically an alkane molecule that's in a cyclic ring like this. So this is cyclopentane. That's an alkane, that's an alkene. So they're different functional groups. Okay, let's have a go at spot the isomer. Okay, so what you've got to do when you're looking at this, you've got to make sure that you've drawn an isomer and not the same molecule, but you've just drawn it in a different shape, because this is the kind of the difficult thing I think with drawing isomers. A lot of students will kind of write it out and they've just changed the kind of shape of it, but in all honesty, it's just the same molecule. So you've got to be really sure here. And the key thing when you're doing isomers is you've got to find the longest continuous chain of carbons, irrespective of the shape. It can be zigzag, it can be upside down, it can be vertical, horizontal, diagonal. It doesn't matter how you draw it, you've got to find the longest continuous chain. Okay, so let's have a look at pentane. And this one is still pentane. Okay, it looks different, doesn't it? It looks very different. But the longest continuous chain in both of these molecules is exactly the same. Yep, so the longest continuous chain, 1, 2, 3, 4, 5, and that's there. Now that looks different to that, but both are exactly the same. It's not an isomer because the longest continuous chain is the same. Okay, so let's have a look at some other types of isomers, and these are called stereoisomers. Not the same type of thing you listen to music on. And these are called cis, or sometimes known as cis or trans isomerism. Okay, so stereoisomers have the same structural formula, okay, but they have a different arrangement of atoms in space. Okay, and this is what we mean by a stereoisomer. So an example of a stereoisomer is a cis-trans isomer. So, for example, we've got these normally exist with obviously double bonds with alkenes, okay? So you've got a C double bond C, and the atoms are bonded directly to this are actually flat. They're planar, okay? So it's not sticking up all over the place, it's just completely flat. So the shape of the C double bond CH is trigonal planar with an angle of 120 degrees. So this is an example of an alkene. You would have seen the bond shapes again. I think this is in topic 3, I think, bonding, the bonding topic. So this is a planar molecule, okay, trigonal planar, and has a bond angle of 120 degrees. Now, atoms can't rotate around this CC double bond. So normally these will spin around. So it's a bit like having, for example, I don't know, a pencil, and you've got things attached to either end of the pencil. Now you can spin that round and they will spin around as well. But if you had two pencils kind of strapped together, it's really difficult for these to twist around around the carbon. So it's rigid. And what this means, because of this rigidity on the double bond, it means you can actually get a type of isomer, a stereoisomer, which is cis-trans isomerism. So let's have a look. So there's your double bond there. Okay, so you've got your CC double bond, and you've got a CH3 and a H on this side, and you've got a C2H, a CH2 and CH3 on this side, and a H on this side. So this double bond here, normally if that was a single bond, this carbon would spin around, and that one could spin around as well. Because that double bond's in there, effectively it braces the two together, and these molecules on the branches here are in fixed positions. They can't move because this can't twist around because of that double bond. It like strengthens it. So that's one isomer, and this is the other isomer. Now you can see the molecules are kind of the same. You can see that just this CH2, CH3 is now down in the bottom, but the hydrogen is at the top. Now this would have been formed, these would have been formed separately from separate compounds during a reaction, and it just so happens that this reaction is ended up like this, with this group down in the bottom left, and it's happened to be that this reaction, this group sits on the top left on this side. So they actually have the same structural formula, but we can't twist that double bond to turn one isomer into the other, so they're kind of distinctly separate, as you can see. So let's bring them two isomers back. So these are have restricted rotation around that double bond, as you can see there. So we get what we call cis-trans isomerism, where we have two different atoms or groups of atoms on the same carbon. So you can see here we do have two different atoms there, or groups of atoms on that carbon there, and we do have it here because that's a CH2CH3 and a hydrogen. That's a CH3 and a hydrogen. So they're two different groups on that carbon there, and they're two different groups on that carbon. So this can have cis-trans isomerism. Okay, if these were two hydrogens, you couldn't have that. So we can name these molecules as either cis or trans. Now cis means same side, so just kind of remember that. So cis means same side, so the same groups on the same side of the double bond, and trans means the opposite side. So this is same groups but opposite the double bond. Okay, so you've got cis and trans. So let's have a look. This one is cis-pent-2-ene. The reason why it's cis is because these are on the same side of the double bond. There's the double bond, and they're both on the top bit of the double bond, aren't they? This one is trans-pent-2-ene, because you've got this molecule is opposite this molecule on the double bond. So it's not on the same side of the double bond. One's below it and one's above it. So that's why that one is called trans-pent-2-ene. So these are what you call stereoisomers. So you can also call them Z, which is same side, or E, which is opposite. And this is actually German for zusammen, which is Z, and E is entgegen. So if you study German, then you probably might be a bit more familiar with that. But they can also be called Z or E as well, which is basically the same principle as this. Okay, for the purposes of A-level, it is. Right, so let's have a look at some optical isomers. So this is another type of stereoisomerism. So there's two types. You've got cis and trans, and then optical isomerism. Now you'll do a lot more of this in year 2, but this is just introducing it, as I say. So optical isomerism is a form of stereoisomerism, and they have the same structural formula, but different arrangement of atoms in space. Okay, so I'll show you, this is my hands, as you can see. I'll kind of show you that in a moment. I hope it works, actually. So optical isomers are mirror images of each other, and they have something called a chiral carbon atom in the middle. Okay, so a chiral molecule is something that has 4 different groups attached to a carbon atom, and then we can arrange these groups in 2 different ways, and this forms 2 different molecules. And we call these enantiomers. Okay, all will become clear when you see an example. So these enantiomers are mirror images of each other and are non-superimposable. Okay, so no matter which way you turn them, they will not overlap. Okay, so a classic example are hands. Okay, your hands are chiral. They have a chiral center. They're mirror images of each other, and they're not superimposable. So you can see the hands on there. There we are. Okay, so you can see the hands that obviously show in there, and you can see they are mirror images of each other. Okay, so they're both hands. They both have a thumb and 4 fingers, but they are actually mirror images of them. And if you put a mirror line down the middle there, you can see they are kind of, they have a chiral center. And chemistry, molecules can have that as well. They can have a chiral center. So what we need is 4 different groups coming off a carbon atom. But when we say non-superimposable, this is what we mean. There we are. Okay, so did you see that? So I'll play it again. There we are. So we put them over the top. It doesn't actually superimpose, and that's it. Looks quite broad, doesn't it? I don't know what's happened to my fingers. Anyway, right, so that's basically saying they're non-superimposable. They won't actually kind of superimpose above each other. So let's have a look at this in a chemistry term then. So we've got these 2 molecules. These are also enantiomers of each other. Okay, so there's your mirror line there, and you can see it's effectively a mirror image of the molecule opposite. But if I move this molecule across and twist it round, it won't actually ever superimpose on the original molecule. And that is your chiral center, which is in the middle there, and you have 4 different groups coming off that carbon in the middle. That's all you're looking for. It's a chiral center with 4 different groups coming off it, and then you'll have a chiral center, which is obviously a mirror image of each other. Okay, so let's find the chiral center. Okay, so first we need to find the chiral center, and then we need to draw them as a tetrahedral 3D shape to show them as enantiomers. Okay, so enantiomers, remember, is the pair of optical isomers. So first of all, here's a molecule here. We're going to see if it does have a chiral center first. So the first thing we need to do is find the carbon atom with 4 different groups surrounding it. So see if you can spot it. I'll give you a moment to pause the video if you wish, and you can see if you're right. Okay, so there's one. There's another group. There's another group. And there's another group. So your chiral center is bang there in the middle. Okay, so you've got 4 different groups surrounding that carbon center. So we found our chiral center. Then what we need to do is draw this as using a tetrahedral 3D shape. So this was back in topic 3 when you looked at obviously structure and bonding and you looked at the shapes of molecules. We need to draw this as a 3D shape. So here it is. There. Okay, so remember the wedge shows something coming towards you, dotted line going away, and then you've got your 2 solid lines. It doesn't really matter which way it is as such, as long as you draw it like that though, with a wedge and a dotted line and 2 solid lines there. Okay, that's your 3-dimensional shape. Then we need to draw a mirror image to show both of the enantiomers. Okay, so we're going to draw that and its mirror image. So basically it's just, you can see, you know what a mirror image is. You can see this is a mirror image of the 2, can't you? So this is basically how you turn a molecule like this to demonstrate in the exam. They might say, can you draw the 2 enantiomers of this molecule? You need to identify the chiral center, draw it out as a 3D shape, tetrahedral, and then it must be tetrahedral, and then draw it as a mirror line and draw the 2 kind of mirror images of each other, and there you're both enantiomers there. Okay, it is possible though, some molecules might have multiple chiral centers. You don't just have one, and you can have more than so you can have more than 2 optical isomers, I suppose. So a classic example in this here is ascorbic acid. So this is also known as vitamin C. And obviously vitamin C, as you probably know, is found in oranges and lemons and limes and citrus fruits. But vitamin C has loads of chiral centers. Again, see if you can try and spot them in that molecule there. Okay, so remember, we need to look for carbons with 4 different groups attached to it. So see if you can try and spot it. You can pause the video if you want. Okay, so there's one there. Okay, so this is chiral because the carbon is immediately bonded to an OH, which is obviously on the side there. There's your OH. It's got a hydrogen, obviously there. This is a skeletal form. There is a hydrogen there. There's a CH2, which is there. Okay. And there's your CH2 is down here. And then you've got your CHO, which is over here. Okay. So that's the chiral center. There's another one. Okay, and this is definitely chiral as the carbon is immediately bonded to an O, an H, a COH, and a CHOH as well. Okay, so these are definitely all chiral. So the key thing is to look for a carbon with 4 different groups coming from it and go as far along as the line if you want. So this one could have 2 enantiomers each, okay, for each of them. So that's it. So that's an introduction to AS level organic chemistry. Like I say, the rest of the topics for the rest of year 1 are organic based, so you're going to go into that in a little bit more detail. Please subscribe to my channel. There's loads of other videos on here for the full A level for CIE. It really helps just to support the channel, and that would be great. Like I say, these are available to purchase from my TES store. I've bundled all the organic ones for year 1 together, but you can buy the full year 1 and year 2's set of slides if you wish. Great for your revision. They're in the link in the description box below. That would be brilliant if you could do that as well. All right, that's it. Bye bye.